I'm going to present a computational study, so the previous thing that happened was not a very good thing to happen, okay? Well, in this study, I'm going to try to answer two questions, okay? We know about chemical statins, okay? And we know about Lycopene. There are some bioactive compounds in tomato, okay, such Lycopene, chlorogenic acid, and naringenin, and there are many different studies in the literature that show that these compounds could provide a moderate hypocholesterolemic effect due to the inhibitory action on this enzyme, okay? There are several hypotheses about the potential mechanism, but there is no evidence right now. So it is not clear how Lycopene exercises its biological activity, okay? So we will try to answer that question, okay? This is the first question for us. And the other one, can we use computational approaches classically used for drug discovery, okay, for the study of these kind of problems? Okay, so let's see. Basically, I'm going to introduce what drug discovery techniques consist in, and then if they can be applied to this problem, okay? So basically, in the drug discovery process, this is a very long and complicated problem that can take lots of years and so on. You identify a disease, a biological target is identified, and then using such methods, a hit candidate is identified, and then test in vivo, in animals, and so on. Okay, so basically we focus on the application of computational methodologies on this part. Okay, once the target is identified, let's see what we can do and discover new compounds. This is the classical approach in drug discovery. Well, how is it done in the laboratory? In the laboratory, we have high throughput screening machines. They are very expensive, they are automatic, they are very time consuming. So we test a lot of different compounds, okay? But, you know, you have these problems. So one alternative is to use virtual screening techniques. What it is? This is the simulation in the computer of this process, okay? So we have identified a target, an enzyme, or whatever, okay? And then we screen a database that contains millions of compounds, okay? And we try to predict whether the compounds will be active or not, and other factors, okay? A more precise definition is the use of high-performance computing. We need to have access to supercomputers in order to perform such calculations, okay? And as an example, you use database of compounds that contains up to millions of compounds, okay? So, virtual screening techniques, there are many different techniques. I just want to show you that all the different techniques can be divided into two great families. The best case is to have information about the enzyme or the target, and the structure information. If we know the structure of the enzyme, we can go in that direction and perform protein ligand docking, which is the technique I'm going to show you now about. Okay? We can also apply molecular dynamics, quantum mechanics methods, but protein ligand docking methods is the tool we are going to use in this study. Okay? So, what can we do? This is an example. This is the kind of interactions established between streptavidin and biotin. Okay? At the molecular level, this is biotin, and these are the side chains from the active side of streptavidin. Okay? Using physical chemistry intuition, we can see that there are why this compound interacts so tightly with streptavidin. There are many different interactions. We can see here clearly hydrogen bonds between the different residues, okay? Some electrostatic interaction, some hydrophobic interactions, and so on. So a computational methodology should be able to understand and predict and quantify this kind of interactions, okay? How? Basically, we apply all knowledge from physical chemistry, okay? So all these interactions are calculated during the simulation. I'm not going into the detail. I'm going to show you a movie that shows how the docking process is is simulated. Okay? This is again for streptavidin and biotin. So in this docking simulation, we are going to try to predict what is the final pose biotin adopts when it enters into the active site of biotin. At the end of the simulation, we can see here, this is the real pose obtained from the crystallographic structure, and this is the pose during the simulation. Now it's trying to to calculate the pose with the highest value for the binding affinity. Okay? So at the end of the simulation, this is what we get. What does it mean? That our prediction is rather good. Okay? Before the simulation, we don't know where the final pose is located. Okay? So during the simulation, we try to calculate for all different possible conformations of the ligand, the binding affinity, the free energy of the union between the ligand and the enzyme. Okay? So this is the kind of information a docking simulation can give you. Binding energy, estimation about the binding energy, and also the structure of the ligand into the binding pocket of the enzyme. Okay? So now I'm going to show you how we have applied this methodology to a classical problem in drug discovery. Okay? We work with the medicinal people. They were interested in the anticoagulant therapy. Okay? So in this case, this is the anticoagulation cascade. There are many different targets, and we wanted to focus on antithrombin. Okay? For antithrombin, it is well known, a good compound is heparin. Okay? This compound interacts into the binding site of antithrombin, and it regulates the anticoagulant cascade. But this compound has some problems. For instance, this is a healthy subject, okay? But people with mutations on this part, this is heparin, a pentasaccharide, okay? So in case of mutations, the interaction is broken, and these people have problems. And also there are some side effects with heparin, administration, and so on. So we wanted to discover a new compound that will not have these limitations. So what we did, we prepared all the simulation. I'm not going now into details. And then we used a database of chemical compounds, everything in the world, okay? Well, not everything, but just around 13 million of compounds. Then we performed the calculation, and for each of these compounds, we tried to predict the binding affinity, okay? So we know that for heparin, using our methodology, this is the value of the affinity. So we need to find compounds with lower value of the binding energy. So after the computational screening that was performed in a supercomputing during three months, we selected just 10 compounds, okay? This is a simulation. A simulation is very nice, but afterwards, you need to test it in the lab. So we bought these compounds, we sent them to the people from the Faculty of Medicine, Universidad de Murcia, okay? And they tested in the lab, okay? The prediction said, hey, you have here a compound that has lower binding affinity than heparin. Let's see if this prediction is good. Okay, so they performed all the experiments, isothermal titration calorimetry, intrinsic fluorescence, and so on, and we were happy to see that we obtained a compound with lower affinity than heparin. This is heparin, the pentasaccharide. It needs a lot of interaction with the side chains from the active site, as you can see here, mainly hydrogen bonds and electrostatic interactions, and this is the compound that we discovered. Okay? This is much smaller, so we will not have problem with mutations on the active site, okay? And we have more potency. Okay? What I wanted to show you with this is that drug discovery techniques that we are using work when you have information, structural information about the enzyme, about the protein, okay? Now, the question is, can we use this kind of computational approaches using drug discovery, but not for drugs, but for the study of bioactive compounds present in food? Let's see. So now we are interested in this problem, okay? We know that statins are drugs that used to lower the level of cholesterol in the blood by reducing the level of cholesterol in the liver. So basically, we have HMGCoA, okay? And when this interacts with this enzyme, then cholesterol is produced, okay? But statins are compounds that have higher affinity than HMGCoA to the enzyme. So once they bind to the enzyme, they block this kind of interaction. Mevalonate is not produced and no cholesterol. Okay, cholesterol is reduced. Okay. So this is a paper from 2001 in Science. This is a very interesting study. Okay. And this is a very classical study, how to develop statins for lowering cholesterol. This is classical rational drug design approach. What does rational mean? Rational mean that we focus, this is HMGCoA, this is the structure. So we try to produce a variation of this compound and try to get another one with higher potency. So basically, we get here a similar scaffold, and then we add different substituents. Okay? Then we go from micromolar, this is 4 micromolar, to some 5 nanomolar. 1,000 times more potency. Okay? So this technique is good, okay? But the problems are, this is slow. Okay? You need to perform a lot of tests. You have to synthesize all the compounds. Sometimes it's very hard to synthesize. And even if you get a very interesting compound, it will be very complicated to sell it, or it will be very, very expensive. So which other alternatives would we have in literature? This is the problem, the situation we had at the beginning. We know that compounds are present in tomato, such as lycopene, chlorogenic acid, and naringenin, provide a moderate hypocholesterolemic effect due to the inhibitory action. Okay, so can we change from the previous chemical statins to this compound? Yes, there is evidence in the literature. But why? What is the mechanism? Okay, well, we are going to give you some answer. Okay, so. You can get here all experimental details about the study. So some rats were fed. There was a control group with normal food, and then an intervention group with a lot of tomato. Okay. So the final result, the main result of the study was that the intervention group contained cholesterol, got to the liver. Okay, could cross all the barriers. Okay. And there we observe cholesterol, and also that lycopene was there, and the production of cholesterol was reduced. This is the experimental result of the study. And now, why? Okay, so now we're going to give you some answer using drug discovery techniques. Okay, so then we examined tomato and the main active compounds. This is the quantity. Okay, so we realized that we have mainly lycopene, chlorogenic acid, and naringenin. Okay. Then we use our drug discovery techniques, and this is our computational control. What does it mean? It means the following. These are the molecules we are interested in: HMGCoA, lycopene, chlorogenic acid, and naringenin. And these are the experimental values for the free energy of binding affinity. If our methodology is going to work, it should predict a binding affinity very similar to the experimental one. So after performing all the calculations, there were only experimental results for this and this, okay? No experimental result for the binding affinity for chlorogenic acid and naringenin. So our prediction was very, very close, okay? So it means for us that we are happy with the methodology, and then we can continue our study. So what do we do now? Now, we get the structure of the enzyme, and we perform these kind of docking simulations, and try to understand, try to calculate here. You can see that the lycopene has a much lower binding affinity than HMGCoA. What does it mean? It means that it should displace HMGCoA, okay? So why? Okay, then we analyze the docking results. We analyze the results of the molecular modeling simulation. And briefly, this is the total binding energy, and here are the different energetic contributions, okay? So I'm going to try to explain what this means, Okay, this is for HMGCoA. This is the total, these are the colors, total predicted binding energy. For Lycopene, we have much lower binding energy, so it means more affinity. And for these other compounds, which are also present in tomato, we have similar or even lower binding energy. So it means these three compounds could displace HMGCoA. And now, and the reason is why? Because the following. This is the explanation that we propose. These bars represent the different physicochemical interactions, van der Waals interactions, solvation energy, hydrogen bonds, electrostatic energy, internal energy, and energy of entropic losses. So what does happen with HMGCoA? It has, if we compare it with Lycopene, it has kind of similar van der Waals interactions, kind of similar solvation energy or stabilization. But here we have a penalty. Why this penalty? This penalty is due to internal energy. What does it mean? It means that for HMGCoA, this is the structural, previously I showed to you energetic results. This is structural results of the simulation. This green thing here, this is HMGCoA in the binding site. This is experimental result, okay, from PDB database, okay. This compound, in order to get into the binding site, it needs to get like this, okay. So this conformation is not good for the compound, and this is the reason of this penalty. And to this, it does not have so much lower affinity, okay. But from the other point of view, this is Lycopene. Lycopene can introduce very well into the binding site of the enzyme. So this is, from our point of view, the explanation. Mainly, the stability of Lycopene is due to van der Waals interactions and also by solvation energy. The compound is highly hydrophobic, so it introduces very well into the binding site of the enzyme. And now, what about these other compounds? The explanation is different, okay? This is naringenin, and this is chlorogenic acid. This green thing here is, again, HMGCoA, okay? But if you see here, this is chlorogenic acid. This part of the molecule mimics really well, okay, the hydroxy groups used by HMGCoA to establish these hydrogen bonds here. This part is very similar, but the molecule is much smaller. It needs, so finally, for this molecule, it is much easier to introduce into the binding pocket than to this bigger molecule, which also needs some torsion and some tension. So these are some of the structural reasons that why these compounds and these get much lower binding energy than HMGCoA. So they can block the interaction of this with enzyme and lower the level of cholesterol, okay? So these are the main results of the simulation, and this is our conclusions. The cholesterol lowering effect of tomato is mainly due to the lycopene content. Why? Because this is the only one that gets to the liver, okay? Chlorogenic acid and naringenin are in very small quantities. They're there, but we have checked that lycopene can get into the liver, okay? And then this compound can inhibit activity of the rate limiting enzyme of cholesterol biosynthesis. So that's the main reason, and we have explained the kind of interactions that are established between this compound and the enzyme. So another conclusion is that computational drug discovery, used classically for the discovery of new drugs, can use also to understand results obtained in other fields, like for instance, food chemistry and other fields, okay? And also we see collaborations where we can offer our expertise in computational drug discovery or development of molecular modeling techniques or analysis of biological data, okay? So thanks for your attention, and also to the people that give us the money for performing this research.
For protein based on in silico modeling, then I think you need to perform some kind of experiment to confirm direct interaction between protein and,
Exactly.
ligand.
Exactly.
using SPR or whatever, you know, experimental technique. Have you ever done any experiment that's
yeah, exactly. The experimental result, the main experimental result that we have here is that you get rats, two different sets of them. So at the end, you analyze the content, the final content of cholesterol in the liver of the rat, and you get that the rats that were fed with tomato get lower content of cholesterol. Okay. So, but your question is another one. Your question is, I think, if we have done a set of a just in vitro experiment with just the enzyme and Lycopene. No, but I want to do it because that will be the final evidence of this study. I agree.
I have one more question.
Yes.
You showed that Lycopene has higher affinity to HMGCoA reductase compared with endogenous substrate HMGCoA based on your calculation. But what about hepatic concentration of HMGCoA and Lycopene after eating tomato? Because even though Lycopene has higher affinity, its concentration is low, then there's no chance that Lycopene compete with HMGCoA. Now, HMGCoA is endogenous metabolite. So
yes, exactly.
Me,
I understand your question. Here, at this point in the docking simulation, we compare just the same, let's say, concentration. Same enzyme, one molecule of the endogenous substance and one molecule of the Lycopene. In order to get the effect of the concentration, of the different concentration, we should provide molecular dynamics simulation, which is another step, another next step for this research. Thank you. You are giving a lot of ideas for new papers.
Okay, thank you.
Very nice job. Yes, I'm agree with that question that made the guy. You need to do the construction of some mutants of the enzyme to check really if the interaction is real or not. This is extremely important.
Yes, I agree.
And the other question is, have you ever checked to give these rats Lycopene plus any other statins to see if because when you change concentration of statins until a certain level, you increase the activity of the drug. So if you mix both of them, this could give you an idea in vivo that whether when you mix, it's the same,
Yeah, exactly. I think this is a very good idea, and that we should also perform that part. Okay. I have also to say that we have been only in charge of the computational part. The experimental part has been done in collaboration with another group from the Faculty of Medicine. But that idea is very interesting, and we should try to consider it.
When you study or when you develop a computational scenario for physiological effect of a bioactive compound, for example, here Lycopene and chlorogenic acid, both have different structure. Both have different structure,
yes.
And the metabolic pathway, like the transportation of these molecules in our body, totally different. One soluble in fat, the other one it's a polar compound. How to overcome this limitation when you develop your computational model?
Sorry, I did not understand the question.
So what I'm saying, the compound you are studying, Lycopene and chlorogenic acid, both are different in their structure.
Of course.
One is Lycopene, which is fat-soluble compound. The other one is polar compound, chlorogenic. And their metabolic in our body, totally different. So how you overcome these differences when you develop your model, computational model? Have you given it a thought, or?
No, at this point we have only focused. This is the model that we propose here, that we focus only in the interaction with this part of the enzyme. Yeah. Of course, we should do a posterior experimental validation and in vitro experiment where we have only this enzyme and other. But of course, this happens the same with other drugs and so on. We should try the modeling with another targets or enzyme involved in the metabolic pathway.
Yeah, because it could be a totally different story when you do it in vivo. Because in vitro, yes, you're focused on the interaction between the two molecules, enzyme and Lycopene, or enzyme chlorogenic acid. But in body, in vivo, in animal, it will
Exactly.
be a totally different story because of their structure.
Exactly, I agree completely. Many different things could happen with lycopene, interacts with other enzymes, and we should take into account all these effects. But in this part, that will be a huge study of all potential. So we focus on this part just on this enzyme. Thank you.